Okay, so yeah, sorry about the delay. I got a puncture cycling in, so that sucked. Anyway, so just to go over a little bit at the end of last lecture, which we didn't really finish. So we were talking. We were talking about the impacts of weathering on climate. So usually you think about, the amount of weathering would be dependent on climate, and that you get like it's hotter and wetter, you might get more kind of chemical weathering that's going on here. This is some granite, some soil forming on top of it. But actually, there's a link the other way round through these hideous series of equations. But the key message is that these reactions at the bottom, so this is the weathering of carbonate rocks, okay? This effectively takes, you can think of this carbonic acid, because that's in equilibrium with CO2, that's taking carbon dioxide out of the atmosphere, and you weather silicate rocks, you take 2 carbon dioxides out of the atmosphere, but when you precipitate these products of weathering in the ocean, you release that CO2 back into the atmosphere, okay? So over long time scales, these kind of cancel out, but these are a net sink of CO2 out of the atmosphere. Okay, so one thing you might want to think about is what happens when these are not in equilibrium. So when the amount of weathering does not equal, at the bottom here we've got the amount of calcium carbonate precipitation. I've got a little, the picture at the bottom, behind this thing is the Grand Bahama Banks. You can see here that there's a huge amount of kind of really shallow tropical water around these islands where lots and lots of carbonate is being produced. So if you imagine what would happen if you suddenly increase the rate of weathering, okay, the amount of carbonate precipitation might not be able to keep up. So then CO2 will be drawn down out of the atmosphere. Or if you suddenly change kind of the way that the Earth works and you suddenly increase the amount of carbonate precipitation, so the amount of corals that are growing or the amount of foraminifera that are being precipitated on shallow tropical areas like this, then you might think that if you suddenly increase that without increasing the weathering, then you might increase atmospheric CO2. So these are things that can happen. So an example here is, so this is kind of approximately what global sea level has done, broadly speaking. So it's gone up and down on much shorter frequencies, but kind of 100 million years ago, sea level was a lot higher than it is today. Okay, you might think about some of the reasons for that. So this is kind of some cartoon schematics. So perhaps if you increase the rate of mid-ocean ridge spreading, okay, that makes the mid-ocean ridge bigger. Okay, so that displaces more water and puts that water onto the shallow kind of continental margin edges. That creates a huge area of ocean that is kind of ready for carbonates to start growing on. So coral reefs, that kind of thing. So that's going to drive CO2 up. Okay, because you're putting out of balance that weathering and carbonate precipitation. So you're getting more carbonate precipitated, so CO2 will go up. As well as you're spreading the ridge a bit faster. Okay, so that means you're increasing the rate of volcanism, which means you're adding to that kind of long-term geological flux of CO2 up into the atmosphere. So we've got these feedback things. So if we had a warmer climate like this, okay, we might expect the temperatures to be kind of warmer in the polar regions, okay, if you've got an overall warmer climate. That might mean you lead to more ice sheet melting, okay? And if you have less ice sheets, or less ice sheet, fewer ice sheets, that would lead to a lower albedo, okay, because the ice sheets are very reflective. The ground that is kind of left behind when the ice sheets melt away is not very reflective. It's kind of like a dull, kind of browny colour. And that means that your climate will warm even more. So in this case, this is a positive feedback loop. Okay? And you could have an initial cooling. You imagine having initial cooling, you have, well, more ice forms in the high latitudes. And then that reflects more solar radiation. That means the planet gets progressively cooler. So you can start off with a relatively small climate forcing, and through positive feedbacks this time, so we were talking about negative feedbacks last time with the weathering cycle, these positive feedbacks can amplify small climate forcings. Okay? And I've just put this little question at the bottom here in terms of when we're thinking about these forcings, think about, if we suddenly had more snow cover over Europe, something like that, right? Then that would make Europe colder because it would reflect more radiation back out to space. Okay? But if you think about what happens in somewhere like the Arctic, if we made the Arctic winter more snowy, okay, so there's more snow over the Arctic winter, do you think that would change the albedo? Certainly would change the albedo. Does it matter? How much solar radiation is there in the Arctic in winter? None, right? The sun does not rise above the horizon. So it doesn't matter how shiny the Arctic is in winter. It matters how shiny the Arctic is in summer. Okay, so you have to think about not only kind of how shiny the planet is with these feedbacks, but you've also got to consider where they're shiny in terms of, you know, is it the equator, or is it the polar regions, or is it the temperate latitudes, because they have different amounts of radiation coming into them. But also the season, okay, because if you have lots of like change in the albedo in winter in the northern hemisphere, in the high latitudes, it matters a lot less than changing the albedo in summer in the high latitudes. Okay, that's very important. Okay, so that was should have been in last lecture. So what we're going to do now is we're going to talk a little bit about some of these shorter term climate variability. So we talked about this long term climate change over hundreds of millions of years through the balance of weathering and volcanic emissions of CO2, and we're going to go on to progressively shorter timescales. So this is just zooming in on the last 60 million years, and you'll notice now that the time moves in the geological way. So this is young and this is old, so time is moving to the left, which is wrong for a physicist. But over this time, okay, we've got this oxygen isotope proxy for temperature. We can see that maybe 50 million years ago over here, it was a lot warmer than it is now. Okay, and the climate's been essentially gradually cooling over that period there. And we can look at some of the reasons for that, and we kind of just really went through that at that time there was more mid-ocean ridge spreading. Okay, and we've got evidence from that. You should have probably covered in Earth dynamics with the seafloor magnetic stripes. Okay, so if we had more volcanism in the past, okay, we had more spreading ridges, we'd have more CO2 being pumped into the atmosphere, okay, and weathering would eventually catch up with that, okay, but that would also be fighting against this increased carbonate production on these flooded continental shelves, okay. So as we reduce the volcanism through time, okay, we're cooling the planet. As we're basically reducing the amount of CO2 in the atmosphere, okay, we're changing the emissivity, and that's cooling the planet. Long-term changes. Okay, other things that have happened over this time. Okay, so we've had continental collision. Okay, so this is India, and that's gradually been moving up into Asia and forming the Tibetan Plateau. Very high mountains, lots of steep slopes. Okay, so those of you who went on the Hollywood Park field trip should know the evidence for this is from paleomagnetism. Those are holes that were drilled in the rocks. Some of you would have seen those, some of you would have not. Doesn't really matter. But anyway, so we formed a big mountain range here. And that kind of happened around kind of 20 to 15 million years ago, that building of this enormous mountain range. So that is going to cause there to be, and this mountain range is in kind of like near the tropics. Okay, so when we increase our physical erosion because of this big mountain range, okay, that's going to lead to more weathering. It's going to lead to a drawdown in CO2. So there's a number of different reasons for gradual cooling over time. Another one is, so we've talked about these kind of like large-scale budgets between, you know, inputs and outputs of CO2, okay? But there's also kind of like an internal kind of mechanisms which are not in our simple model. So remember our simple model for the temperature of the Earth's surface? It's kind of S0 brackets 1 minus alpha over 2 sigma my brackets 2 minus little e all to the quarter power. Yeah? Yeah, I can remember it, so you should remember it. Top tip. Anyway, so there are things that are not in that model that affect the climate. So that's a very simple model. It doesn't really account for everything. So one of the things is this redistribution of heat around the Earth. Okay? So this is an example here. So this is Antarctica. So at some point, this gap between South America, it was pretty obvious, this gap here, okay, at some point this gap wasn't there. Okay, so this current, which is basically the strongest ocean current currently in the world, that whizzes around Antarctica, okay, that current didn't really exist until that hole opened up. Okay? And as soon as that hole opens up, that basically isolates the South Pole. Okay, so once you have this current whizzing round and round and round, it's very, very hard for heat to get from up here to down here. Okay? Okay, so that kind of means that so before that boundary was kind of that current, the Antarctic circumpolar current, if you want to know kind of what it's actually called, before that existed, the South Pole was relatively warm. Okay? Right? But as soon as you start that current up, you open up the Drake Passage, that gap between South America and Antarctica. That means you isolate Antarctica from the warm tropical kind of source of heat. So that means Antarctica gets much colder. Okay? So that means you can start to develop an ice sheet on Antarctica. Okay, you can start to develop extensive sea ice around Antarctica. So that has a positive albedo feedback, so we start to get cooler climate. So the opening up of that Drake Passage is one of the reasons why we suddenly get cooler over time. Okay, and similarly, in the northern hemisphere, okay, there used to be a gap. There used to be a gap here. Okay, I mean there is a gap now. It's the Panama Canal, but there was a real gap where warm water from the Atlantic here could flow through into the Pacific. Okay. And that meant that there was less water flowing north in the Gulf Stream. Okay, so when this gap here was open, okay, there was less heat going up to the northern hemisphere here. So you might think, oh, if you've got less heat going up there, it'll be colder. Okay, but if you've been reading the online discussion forum, you'll notice that ice sheets also require there to be lots of snow. Okay, so in this case, this specific ice sheet, the Greenland ice sheet, can only really grow into a big ice sheet when it has lots of moisture kind of precipitating out on it. So one of the reasons why we have this extra glaciation and cooling across the last 60 million years is that when this gap here shut, okay, we could start to grow an ice sheet up here because we were transporting snow onto it. Okay, so that leads to another positive feedback. Okay, so it gets colder, because this bit up here is white. Okay, so kind of we've got a number of different mechanisms to explain this long-term cooling here. Okay, and not all of those things happened at once. And you can see that there was kind of a change here, then maybe a sudden change, and then another sudden change there. But there was a variety of things that happened to cool the climate over the last 60 million years. And what we're going to talk about now for the rest of the lecture is kind of the even shorter timescale. So we're just going to move down for the rest of these lectures onto shorter and shorter timescales. So this graph here at the top, again, we're using oxygen isotopes as a proxy for essentially global temperature. And these are actually the oxygen isotopes in shells that are living on the bottom of the ocean. Okay, and they do tell us about the global kind of temperature because the deep ocean is fairly homogeneous in terms of temperature compared to the surface ocean, and the deep ocean basically gets to the deep ocean from sinking at high latitudes. Okay, and then you'll go through this in other courses, but basically we're not directly measuring the global temperature, but it's a kind of a proxy of global temperature. Once again, you'll notice the oxygen isotopes are negative up, so 2 is less than 4, but I mean that's kind of irrelevant. But the key thing about this is that when we look at the deep ocean, and therefore a proxy for the global climate, or at least the high latitude climate, we have this really high frequency variation over the last 5 million years. And in fact, this variation has been going on for almost all of Earth history in the climate. So it switches between warm, cold, warm, cold, warm, cold on a 40,000 year cycle and a 100,000 year cycle. So geologically very, very short. So this is kind of this cartoon. We're going into these kind of shorter timescales. And this is just even zooming in a little bit closer. So this is the last 100,000 years. And you can kind of see that there are cycles of warm, cold to warm, and within that there are also smaller climate variability. Okay, we give these numbers in terms of knowing where we are in geological time. So we call them marine isotope stages, but that's not really very relevant, and we just number them going back in time. So this is the first one, second one, third one, fourth one, fifth one, and this is the fifth one. So it's not really terribly rigorous how they're numbered, but you'll see these terms coming up quite a lot in the literature in further courses. These ones over here are maps of the amount of ice. So this is now, and this is 21,000 years ago. So this is the last time it was really, really cold, marine isotope stage 2. And you can see that there was much, much more ice 20,000 years ago. Okay, so this is 5 kilometers of ice over Canada. So that's a huge amount of ice. Greenland was a little bit bigger in terms of ice. All of Iceland was covered in ice. It's kind of in the name. Northern Britain, should we call it, or Scotland, completely covered in ice. A bit of Ireland, and almost all of Scandinavia and bits of Russia covered in ice. So huge amounts of ice stored on land. So sea level, so all that ice has got to come from somewhere. So that the sea level was actually almost 120 meters on average lower around the globe, which is a huge difference. It was also much colder. So we've got maps here of the temperature, so we can see that parts of the globe were much, much, much cooler. Okay. So what we want to do is try to explain why we have these really high frequency cycles. Okay, and the reason we have them is that the Earth's orbit around the Sun changes. Okay, so this was first kind of like figured out by this guy James Kroll, who was from Edinburgh. Okay, and then this guy Milutin Milankovitch came along and did the maths properly. But the idea is that there are different ways that the Earth's orbit can change, and that doesn't necessarily change the amount, the total annual amount of radiation the Earth receives. So that S0 in our climate model, that's not really changing much. But what we do change is we change where on the Earth gets heated and when during the year. And that's important for developing these climate feedbacks. Okay, so we're just going to go through and explain these different ways that the Earth's orbit can change. So there are basically 3 types. There's eccentricity, which is the Earth's orbit around the Sun is not circular, it's elliptical. Okay, so it's kind of squashed out. And the degree to which it is squashed out is called eccentricity. So sometimes it's round, sometimes it's kind of squashed. Then we have this term called obliquity. Okay, so obliquity you can just think of as axial tilt. So the Earth's axis of rotation is tilted over relative to its orbit around the Sun. Okay, and that's why we have seasons. Okay, and that amount it's tilted over changes through time. So sometimes it's tilted over a lot, sometimes it's tilted over less. And then the last one is precession. Now precession is slightly hard to get your head around, but essentially if your axis of rotation of the Earth is tilted over, the Earth is spinning round, okay, the direction at which that tilt points, okay, is precession. So it doesn't just stay pointing in the same direction all the time. The axis kind of wobbles around, okay? So we'll just go and explain it. So axial tilt is kind of the easiest and simplest one to try to get at. So imagine if the Earth's axis of rotation, so imagine the Sun is kind of over here somewhere, way off to the, where that arrow is pointing. If the Earth's axis wasn't tilted over at all, okay, there wouldn't be a summer and a winter at all. Okay? But if the axis of rotation was turned over like 90 degrees, like I think it's Uranus, one of the big planets, then in summer, that one side of the Earth would constantly be pointing at the Sun. Okay, there would be no day and night. And then you'd rotate around to the other time of the year to winter, and you'd be in complete darkness for all of winter. Okay, which would suck. It's like living in Scotland. So basically, the amount at which the axis of rotation is tilted over is determines how different summer and winter are. Yeah? So if it's tilted over a lot, then summers will be really hot. We have long days in summer, but winters will be really cold and we'll have really short days in winters. Okay? So this makes a bigger difference at high latitudes. Okay? Yeah? Because in the equator, around the equator, don't really have seasons. Okay? Doesn't really matter which. It also is when the axis is tilted over more, summer in the northern hemisphere will be warmer and we'll have longer days, and also summer in the winter hemisphere will also be warmer. So they're basically the effect in the northern hemisphere and the southern hemisphere are in phase. They're happening at the same time. Okay, and you see that's not going to be the case for everything else. Okay, so precession. So precession is more challenging to get your head around. So remember that the Earth's orbit is not spherical. Okay, so if we look now at this guy at the bottom here. So the Earth goes around the Sun. Okay, and sometimes the Earth is close to the Sun. Yeah, and sometimes it is far away. Okay, now these arrows here are representing that tilt of the Earth's rotation. Okay, so this is where so imagine we're looking down on the top of the solar system. Okay, and this red arrow is the axis of rotation. Okay, so this means that basically we're at summertime, so we're the summertime in the northern hemisphere. Okay, so the axis is tilted towards the Sun. Okay, so if we now look at what this does to so it's summer, and we're tilted towards the Sun, so it's summer, but we're also closer to the Sun. Okay, so this makes summer in the northern hemisphere warmer. Okay, because we're close to the Sun. But at the same time, or in the same year, we go round to winter in the northern hemisphere. Okay, we're now far away from the Sun. Okay, so that means makes the winters extra cold. Okay, but in the southern hemisphere, okay, it's not the same. Okay, so we've made the northern hemisphere summer down here is warmer, but the southern hemisphere summer, which is up here, is now colder. Okay, so now the two hemispheres are out of phase with each other. Okay, so the effect of precession is basically to change the magnitude of the seasons. Okay, once again, it's more important at high latitudes than low latitudes, but the effect is at different times. So when precession is making the northern hemisphere warm, it's making the southern hemisphere cold in summer. Okay, and lastly, well, that's lost all of that narration. But anyway, imagine that perihelion happens when you're really near the Sun. Okay, that means that season. So perihelion happens when you're near the Sun. Imagine that is summer in the northern hemisphere, because the Earth is pointing towards, like it is in the diagram on the left. That makes that season shorter, okay, because you're going past the Sun faster. But it makes winter longer. Okay, so we have this effect that we're nearer the Sun in summer. Okay, so we're getting more energy coming in, but that season is shorter. So these are quite big effects, being nearer the Sun and changing the length of the season, but they kind of cancel each other out in terms of the total radiation received that summer. So it turns out that the radiative effects of orbital eccentricity are not that great, okay? But they are important for modulating the effect of precession. Okay. So then look at the effect of all these things, and we look at kind of how these things change through time. So at the top we've got basically precession, which is the direction which the Earth's orbit points relative to that position of perihelion. The obliquity, we've got this is how much the Earth is tilting over, and that changes through time. And then we've got eccentricity, which is like the fatness or thinness of the orbit. Okay, so if it's not a direct calculation. We're not just adding up those top three curves and getting the solar forcing, because the solar forcing is different at different latitudes. Okay, because we get lots of energy at the poles, at the equator, less at the poles, and that the amount that you get less at the poles depends on these parameters about how much the Earth is tilted over. But this is basically the amount of radiation that the northern hemisphere high latitudes get in summer. Okay? And the reason we plotted that is because one of the hypotheses about how these all these orbital variations, how they actually affect the climate. So at the bottom here we've got basically another one of these wiggle measures of climate, probably oxygen isotope based. Now, if we think about how we go from that basically forcing curve to this yellow forcing curve to the black climate, it's not a direct. I mean, you can see that they're not the same, right? So one of the theories is that we have this forcing, and that changes how likely it is for snow or ice that was formed in the winter to melt in the summer. Okay? So if we have a cold solar forcing in northern hemisphere summer, that means it's less likely that the snow that fell in the winter will melt away. Okay? So you don't have to melt away also. It could just be in the highland area. So for instance, there's still some snow from last winter in like the Highlands, very small patches. Okay? You imagine if it got a little bit colder in summer, so if our summers were a bit colder than the last summer, we'd have more of that snow remaining over the land. Okay? And that would lead to this positive feedback. So that means that the albedo would be higher, and that would lead to a cooling from our equation. Okay? So basically this solar forcing is really, really a small kick to the climate system, and it's only really kicking it in the high latitudes. Okay? So what it's doing is there's basically we have a forcing, and then there's a whole bunch of climate feedbacks, mostly to do with changing albedo, but also to do with changing CO2 as well. So if it gets a little bit colder, CO2 can dissolve more in water. Okay? So you notice if you open a cold can of beer, it fizzes a lot less than a warm can of beer. Okay, that's because or fizzy pop, whichever. I'm sure you drink fizzy pop. So that means that when it's colder, more CO2 from the atmosphere goes into the ocean. That means that there's less CO2 in the atmosphere, which means it gets even colder. So there are all these positive feedbacks that start to amplify these small climate forcings, okay, that leads to us having kind of a climate periodicity that looks something like this. Now, if you kind of look at the exact form of the climate is not the same as the forcing, but they do have similar periodicities. So if you look in the climate, we have kind of cycles going up and down about every 100,000 years. And if you look at the cycles in eccentricity, there's a kind of a 95 and 125,000 year cyclicity in that. And they kind of average out to be 100,000 years. So there is, when we look at records of climate, okay, we do see the same frequencies of variation that we see in these orbital forcings. Okay? But the forcings are directly controlling the climate. They have to go through these kind of complex feedback mechanisms of albedo change, of CO2 change, and stuff. Okay, so following on from when the fire alarm went off in the lecture, we were talking about these Milankovitch cycles. So these are changes in the direction of the Earth's axial tilt, the way that the orbit of the Earth goes around the Sun, changing from a circular orbit to a more squashed out orbit, and this concept of precession, where basically the direction at which the Earth's axis is tilting changes relative to its position in this elliptical orbit. Okay, so these parameters, these parameters here. So this is axial tilt, obliquity. This is precession, the direction which the tilt is pointing, and this is the basically squashness of the Earth's orbit. Okay, so these changes in the Earth's orbits don't really change the total amount of solar radiation coming in the atmosphere that much. Okay. Because if you tilt the axis over a lot, for instance, you get warmer summers, but you'll get colder winters. Okay, and likewise for the opposite hemispheres, you get warmer summers but colder winters. So most of these kind of effects kind of cancel out Okay, so this term doesn't really change, but the reason why these parameters are so important for changing Earth's climate is because they change the distribution of that incoming radiation around the globe. Okay, so it's either get more radiation at the poles or it's more evenly distributed over the whole Earth, and that has a big effect on some of these other parameters in the climate system. Okay, so particularly albedo. So imagine if we start to have warmer summers. Okay, we have warmer summers. When it snows in the winter, okay, if it's warm in the summer, that snow will melt away. But if we have, say, a cooler summer, okay, and it snowed in the winter, okay, then we would not melt away as much of that snow in the summer, and it's the albedo, or the amount of snow, or the reflectivity of the planet, okay, and that can be changed quite easily by putting snow on it. Now, if you have lots and lots of snow in the winter, that doesn't matter so much because just imagine at the bottom here, if the sun is over here somewhere, imagine this is the sun and this orbit here thing isn't there, and this is the Earth over here. If we're in the winter over here, okay, the sun really isn't shining on this place, so it doesn't matter what reflectivity it is, okay. But in the summer, okay, when the axis is tilted towards the sun, okay, that really matters for how for the albedo of that region, okay. So it turns out that if we have high obliquity, so we're tilted over a lot, we'll have really warm summers, which means it's really hard to accumulate snow throughout multiple seasons. Okay, so that has a feedback effect. Okay, so we go through these kind of feedback effects. So if it gets colder, then we might get so if it gets colder in the summer but warmer in the winter, okay, so overall temperature is not the same, then we might go and have maybe same amount of snow we get every winter, or we might get more, we might get slightly less. But the important thing is in summer, okay, because we've got a colder summer, okay, that snow won't melt away, which means that the albedo of that region in the summer, when it's receiving the most solar radiation, is higher, which means you get more cooling, and that leads to a positive feedback, okay, which actually amplifies these small orbital forcings. And that's just one example of a positive feedback. There are other ones which involve the emissivity. So when the whole planet gets colder, okay, we can put more CO2 into the ocean because CO2 is more, in fact all gases are more soluble in liquids at colder temperatures. So that means if it's colder, we put more CO2 into the ocean relative to the atmosphere. The atmospheric CO2 concentration therefore goes down, okay, leading to a lower emissivity and a colder surface temperature of the Earth. Okay, so that's just to recap how we get these large climate changes due to these small Milankovitch kind of or orbital forcings. Okay, so these are these small forcings, but they are actually causing quite large swings in the Earth's climate. So if you remember back from earlier on the lecture, the climate state up here is kind of how the climate is now. I mean, climate state down here is we have maybe 4 or 5 degrees Celsius colder globally, averagely. So this is the temperature in Antarctica. So we have much more cooling in the high latitudes, in the polar regions. We've grown ice sheets that are 5 kilometers thick over Canada. Sea level is therefore 120 meters low. This is a huge difference in the climate. Okay, and this is all caused by these small changes in the Earth's orbit being amplified through climate feedbacks. Okay, and you can see here that there's this how one of these feedbacks is kind of some of the evidence for that. So this is a record of basically the climate in blue. Okay, so this is measured from some isotopes in Antarctica. I think hydrogen isotopes measured in the ice as a proxy for temperature. Okay, and you can see in this case we've got this is 400,000 years in the past. This is the present, and the blue line has gone through these cycles of glaciation, deglaciation, some big swings in climate. Okay, and this was the last glacial maximum, and this is kind of like now. And you can see, joined with those are changes in atmospheric CO2. So this is CO2 actually recovered from bubbles in the ice. And you can see that these are closely going up and down with this temperature. Okay, so when we have a cold temperature, okay, we have low CO2, okay, and that's because we've got this CO2 feedback. So we've got cold temperatures, CO2 dissolves more in the ocean, okay, and there are other reasons why the CO2 changes across glacial interglacial cycles, but there's this strong coupling that small changes get amplified through a positive feedback involving carbon dioxide. Okay. Okay, so we're now going to look onto even shorter timescales. So we're just looking at, saying we're looking at the last glacial period to the modern. Okay, so we're in a shorter time period than these orbital variations. So the variation we're seeing is too fast to be forced by these orbital changes. But we can see here some evidence for these changes. So these are both ice core records. Okay, so first of all we've got some ice cores that have been drilled in Greenland up here in the ice, and these are down here. These are just two different drill cores, and they've measured the isotopes of oxygen as a proxy for the local temperature. And you can see that this is now, so this is the Holocene, this is the interglacial period we're in now, it's quite warm, and in the glacial period down here, so this is the last glacial maximum over here, this is marine isotope stage 3, remember from earlier in the lecture, and you can see that it's colder in this period. We've got more negative delta oxygen isotope values, okay, and this is kind of working the other way around to the how the proxy is recorded in the ocean. Okay, so don't worry too much about the details of how the oxygen isotopes work, but it was colder in the past. We also have these really rapid changes in local climate. Okay, and you can see these changes are not necessarily global. So we have records from Antarctica here. Okay, and we can see that we do have high frequency variation. So once again, just two different cores drilled in different places in Antarctica. So the now is warmer than the glacial. We do have some variation here, but it's not the same type of variation we have in the North Atlantic. Okay, so this is an example where there are rapid climate changes going on, but those climate changes are not happening everywhere on the globe. Okay, so these are basically where our little model of climate, our temperature of the surface equals the solar flux times 1 minus the albedo divided by 2 times the Stefan-Boltzmann constant times 2 minus the emissivity, all to the power of 1/4. Okay, an equation you should all know and love. So that equation cannot explain these phenomena because these phenomena are not global phenomena. Okay, so this is one of the weaknesses of our model, but nonetheless we can try and think about how we might explain these variations in climate and think about what this means for how the climate system operates. It might tell us something about these climate feedbacks that allow us to explain the temperature of the Earth. Okay, so this is just looking in real, zooming in on a period in basically the last glacial, where we've now got a core from Antarctica, and this is a core from Greenland. Okay, and we can see that basically the way that these isotopes are working, so cold is down on these and warm is up. So we've got these gradual cooling and rapid warmings in Greenland. Okay, and these do appear that they're happening at the same time as things going on in Antarctica, except it looks like it's the other way around. So when Greenland is cold, Antarctica is warm, cold, warm, cold, warm. Okay, and they've got a slightly different shape. Okay, so these are more rapid and these are kind of more gradual. Okay, so that's kind of the observations of our climate records, and we see if we can come up with some kind of like hypothesis to see if this is the way it works. Okay, so this is some other evidence of stuff that's kind of going on in the North Atlantic at these times. Okay, so when we get these really cold events in Greenland, we also find in sediment cores. So this is the North Atlantic down here, and we've taken, well, some other people have taken sediment cores from different places in the North Atlantic, kind of all over the North Atlantic, and what they find in these sediment cores is not just kind of clays and muds that get washed in off the continents, and kind of the fossils of planktonic foraminifera and coccoliths and things that live in the sea. They find these kind of bits of rock. Okay, so these are bits of quartz. Okay, you occasionally get bits of limestone.
bits of volcanic rock here you can see, in amongst the things like this. So this is a foraminifera here. So in amongst the things that you'd expect to find in a marine core, this is another foram here. Okay? And the reason these things are found is because when ice kind of like grinds over the land when it's on an ice sheet or a glacier, it picks up rock from the bottom of the glacier, and you can see an example of this. These are some bits of rock that are caught up in a lump of ice, and these lumps of ice break off the glaciers when they come into the sea, and then this floats out into the ocean down here. Okay, and as it floats out into the ocean, it eventually melts because the water is warm, and that means that all of this kind of rock that's caught up in the ice kind of just falls out and sinks to the bottom of the sea. Okay, and it turns out that during these periods of intense cold in the North Atlantic, we get an enormous quantity of this stuff deposited down here. Okay, so basically that suggests that during these cold periods there are many more icebergs making their way down from Greenland up here and up here, making their way down into this region up here. Okay, so there will also, because it's the glacial, there'll also be glaciers from Iceland, from British-Irish ice sheet, and from the North American ice sheet. Okay, these will all be covered in ice, and they'll all be giving icebergs with lots and lots of rock on them and bringing them down into this region here. Okay. Okay, so one of the things we might want to do is think about why these events are so episodic. Why aren't they happening all the time? Why don't we have continuous flow of these kind of like icebergs from the ice sheets, and why do we have these rapid changes in temperature? Okay, and one of the hypotheses for these changes is actually variations in this this transport of heat from the tropics down here, okay, where it's warm, up into the high northern latitudes. Okay, and some portion of that heat transport, so some of it's in the atmosphere, okay, but a large chunk of this is in this basically this North Atlantic drift current that makes its way up here. Okay, so the Gulf Stream itself is essentially just driven by the fact that the wind blows kind of generally from east to west, and the Earth rotates, and you might cover that in other courses in the future. Okay, so this part of the circulation that goes round and round and round and round is a function of basically the Earth rotating and their winds blowing. Okay, but this limb of the circulation that goes up into the far north, okay, some of this is ultimately driven by wind, but actually some of it is driven by the water when it gets up into the high northern latitudes, okay, in regions around the Labrador Sea and the Greenland Sea over here. It's actually driven by when the water gets up here, it can get cold enough because it starts to lose its heat through evaporation, okay, and sensible heat transfer into the atmosphere. And that causes the water to get colder, and the evaporation also makes it get more salty. That makes it denser, so it can sink to the bottom. Okay, so that sinking water basically creates you can think of it as basically creating a gap, which allows warm water to move up to the northern latitudes up here. So this process of deep water formation, of water sinking, can affect how much heat gets up into this region up here. Okay. So we can think of a situation where, if we want to think about these variations in time, okay, when this flow of water is strong, okay, so when this flow of water is strong, so when we're forming lots of deep water up here in these regions up here, we're drawing heat up to the high northern latitudes, okay, so that causes this part of the Earth to be warm, but because we're transporting heat northwards, okay, that makes this part of the Earth cold, relatively speaking, okay. And likewise, when this transfer of heat is less efficient, okay, so we might have stopped this deep water formation up here, so less heat can get up into the northern high latitudes. That makes this region colder than it usually is, and that heat has to have, basically, you can't disappear that heat, so that means that heat remains down in the southern hemisphere, which means this region is warmer than it would have usually been. Okay, so you've got to think of some kind of mechanism now that would maybe start to switch between these two states of having rapid flow and kind of less rapid flow. Okay, so this hypothesis does kind of explain this kind of anti-phasing between the hemispheres that we saw. So when Greenland is cold, Antarctica is warm. When Antarctica is cold, Greenland is warm. Okay. Okay, so this is one of the possible mechanisms that they've been kind of like hypothesized to cause this switching between these kind of two states. Okay, so we can just talk through how this kind of works. So these diagrams are cartoons. So this is kind of the North Atlantic, and this is kind of Greenland, and this is kind of obviously a section through that in a cartoon way. And this is the water flowing northwards, okay, and we lose heat to the atmosphere, okay, and we also make this bit of water here more salty because we're evaporating water out here, okay. So that causes us to form our deep water that basically exports cold, salty water to the deep ocean, making this kind of flow northwards, kind of carry on being strong. Okay. So what happens is that process would continue. Okay, we carry on kind of transferring heat up into our ice sheet up here, but that increase of heat, okay, also allows there to be high rates of melting. Okay. So that means that we're adding fresh water into this region here. So the stronger this goes, we start to increase this flux of fresh water. Okay. Now, what that causes is if we keep on adding lots of fresh water into this region here, okay, it decreases the surface salinity. Okay. And if the salinity goes down, so it becomes less salty. So salt water is denser than fresh water. So if you put lots of fresh water in here, this water doesn't get as dense as it used to, so this sinking happens less. Okay? If this sinking happens less, that means that we then weaken this northwards flow, okay? Which means we're putting less heat into the atmosphere, okay? Which means that we can grow our ice sheet a little bit more, or maybe reduce the amount of runoff, okay? Okay, and if we reduce the amount of runoff, then this flow here, although initially weakened, okay, can start to strengthen again, okay, which means go back up into this state here. This basically shows how we can switch between one kind of state of the climate where this is kind of strong, and then one where this circulation of water is weak, okay, and basically the switch between the two happens when we add enough fresh water into this northern high latitudes ocean region for there to be the water to be too buoyant to sink. Okay, and you can think as we're basically melting and growing ice sheets more rapidly, okay, we might be changing the amount of carving of icebergs into the ocean, and those are responsible for those layers of increased, we would call it ice rafted debris. Okay, so this is debris that's kind of rafted from the continents out on icebergs into the ocean and then sunk to the bottom. Okay. Okay, so this is kind of another kind of like mechanism that might play a role in this kind of like switching between these two climate states. Is that large ice sheets, okay, they're kind of like they're constantly accumulating ice in snow. Okay, the ice then actually flows towards the sea, okay, where it breaks off and then forms an ice shelf, okay, and then you get icebergs, okay. And this position of where the ice is flowing to is actually quite dependent on the shape of the geology underneath. Okay, so where it comes across a piece of high ground like this, okay, the ice sheet might get a bit stuck, okay, and it might be in a very then stable position. Okay, so you can imagine if you had a bedrock that looks a little bit like this, that had maybe a number of lumps, okay, the ice sheet could be very stable here. You could get a little bit of melting and then nothing really happens, okay? So you get a little bit of melting, so you might get a bit of heat flow from the ocean or some melting from above. That would also thin the ice sheet. Okay, so we get a little bit of melting, the ice sheet stays where it is, but you have more and more melting, and that basically opens up this gap underneath the ice shelf, okay? And this would make this part of the ice shelf very unstable, so we get basically more rapid flow, and then the ice shelf would retreat back to basically the next stable point on the bedrock. Okay, and this would result in these events where we have lots and lots of icebergs going out into the Atlantic. Okay, we're reducing the size of the ice sheet. Okay, so we're basically changing the local albedo by quite a lot. So this would lead to a sudden warming. So we'd have lots and lots of icebergs, ice raft debris, followed by a sudden warming. Okay, so this is another mechanism that could be involved in these rapid changes in the climate in the northern hemisphere. Okay, so I think that's kind of the important thing for these millennial scale changes. But I think an important kind of way that the climate system behaves that you guys should understand is that the response to small forcings, or the response to any kind of forcings in the climate, is not a linear response. So if you push the climate system by changing some of the forcings a certain amount, you don't always get the same response. Okay, so this is kind of diagrammatically explained up here. So if we give the climate, say, a small forcing, okay, so we basically force it a small way, we might imagine the climate system state, okay, to change a little bit. Okay, so this is kind of a linear response. And if we give it the same forcing over here, we would maybe expect to get a similar response. Okay, so this is not how the climate works. Okay, climate work is more like these bottom two figures up here, where we might change the forcing by a little bit when the climate is in one state. Okay, so in the interglacial, perhaps we might change it a little bit, and the climate responds a little bit. Or if we're in the full glacial, we might change the albedo by a little bit, or change the solar flux by a little bit. We might get a little change. Okay, but there are some certain thresholds where the climate appears to be much more sensitive. So small forcings could cause a much bigger change. Okay. Now this goes on to kind of the next level, where actually sometimes you could force the climate a little bit. Okay, and then the climate basically changes a little bit. Okay, but then if the climate state, if you change that forcing back, it will return to its original state. Okay, so you can imagine this portion of this graph up here. You imagine this is maybe global temperature, or maybe even something more like local ice sheet position, or something like that. The amount local, the size of the Greenland ice sheet, you could say, and this could be some kind of climate forcing over here. So this is forcing. So we could maybe our climate forcing could be maybe in this case we could be forcing the size of our Greenland ice sheet with maybe local temperature. Okay, so you can imagine up here the example would be, okay, if this is the size of the Greenland ice sheet, this is temperature. As we increase the temperature, the ice sheet gets smaller, it melts. Okay, but you can imagine there are some times where if you actually increase the temperature, it doesn't matter too much at the beginning because the ice sheet's maybe really, really big. Okay, so most of the ice sheet is at a really, really high elevation. So small changes in temperature, you don't really change much outside of the, you don't bring much of the ice sheet above the melting point. Okay, but if you increase the temperature a lot, you might get to some stable state where you actually really melt the ice sheet really, really quickly. Okay, and then at really, really high temperatures, there might not be any ice sheet left. So the change in the size of the ice sheet is quite small. Okay. Now on this bottom diagram, you might think, well, actually, if we start to grow our ice sheet, if we increase our forcing, we maybe increase temperature, our ice sheet starts to melt. But if we make it colder again, the ice sheet will grow back to its normal size. Okay. But imagine if we start to carry on increasing our forcing. Excuse me, wipe nose. If we increase our forcing to some point where the ice sheet has reduced in size by a significant amount, okay, then with no more forcing, the ice sheet will continue to collapse. So it doesn't matter what we do to the temperature, it will continue to collapse. Okay, so it's reached some threshold, critical threshold, where the ice sheet is now so small, it basically runaway collapses. Now this might be something to do with the dynamics of the ice sheet, or you can imagine as a simple scenario, you've melted enough of the ice sheet so that the land around the ice sheet is now exposed. Okay, that's exposing dark rock, which has got a low albedo, and that's absorbing more solar radiation, so is warming up the ice sheet essentially by itself without changing the global temperature and things like that. Okay, so that means that we've got now the ice sheet moves into this basically other state where it's now much smaller. Okay, for a given kind of global temperature forcing or something like that. Okay, so we've got this state where we've got this hysteresis step here, where we've got you force it for a little bit, it goes back, but if you force it beyond some threshold, the climate would flip, or the climate system, in this case the ice sheet, would flip into a different state where, although the temperature now, if you reduce the temperature back, okay, you can never recover the size of the ice sheet. Okay. Okay, so this is it, kind of, you know, an analogy of kind of rolling balls across a kind of a hill. Okay, so the ball can either be in one potential well or the other potential well, and once you're in one of these wells, it's very hard to force the climate to get you out of them. Okay, so just going to look at a really last example now of really short-term climate change, where this kind of like threshold forcing behaviour. So we're going on to kind of like really short timescales now. Okay, so this is an example from the Sahara in northern Africa. So about 5,000 years ago, the large parts of the Sahara Desert were not, in fact, desert. Okay, they were quite lush grassland. Okay, and there's lots of evidence for that in archaeology. And this is an example here of a carving in some rock of a hippo. Obviously, that's a hippo in the middle of the Sahara Desert. So this is kind of showing that this region was much more habitable for life, was much cooler, much wetter. Okay, so this is this region here we're looking at. Okay, in basically the southern portion of the Sahara Desert. Okay, the Sahel, and you can see that there's a really big contrast here in albedo. Okay, so this is a very dark region. Okay, this is a very shiny region up here. And what changed was basically 5,000 years ago. This region here was essentially like this, was green. Okay. Okay, so these are some data from this region. So at the top you can see what we've got here is we've got forcing. So this is the amount of solar radiation that's being received in this region. So you remember that the orbital variations in the Earth's kind of orbit around the Sun and its axis tilt and all that kind of stuff, they don't really change the total radiation coming in, but what they do is they redistribute that in different places around the Earth. Okay, so in this case, this is the local summer installation. So you can see 9,000 years ago it was warmer, or there was more solar radiation locally, and then over time it's gone down. Okay, so what we've got at the bottom is a climate proxy record from nearby. Okay, so this is looking at a sediment core that's been drilled off the coast of Africa. Okay, and in that sediment core we're looking at how much dust has been blown off the land. Okay, so the important thing here is what we're measuring is the percentage of sediment in that core that is wind-blown dust. Okay, and you see that the axis here is flipped upside down, which is annoying. It's the thing that geologists do. So this means that we've got not much dust blowing off the land over here. Okay, because this is when that part of Africa was kind of lush and green. Okay, so there wasn't much dust being kind of blown off the land. And then all of a sudden, at some point, 5,500 years ago, we changed the climate into this state over here where it's much dustier. So the vegetation is basically mostly gone, okay, and we're basically in this kind of like dust bowl kind of environment, okay. So what's happened here is we've had this gradual forcing, and you can see the effect of that gradual forcing, okay, as basically the climate has started to dry out, okay, as we're basically getting less. In this case, we're probably the solar radiation dropping down is probably causing the climate to actually be a little bit drier, although it's being cooler. It's the moisture supply that is causing this change in basically the amount of vegetation. But we stay in basically the same stable-ish climate. Okay, so we stay in this lush state, although we're changing this forcing, and we stay in that because the moisture is being recycled locally in the trees. So when it rains, the moisture gets stored in trees and in the soil and in shrubs and grasses and all that kind of stuff, and that basically allows that moisture to stay in the environment longer, so it can support the trees and the grass to carry on growing. It also allows it to evaporate more slowly, so it can rain out again more locally again. Okay, so we can recycle that moisture locally and maintain that environment. Okay, but at some point it gets just too dry to do that, and basically the trees and the grasses start dying off because it's too arid, and we basically get this sudden change where we're now in a state where we can't store any more moisture locally, and basically the climate basically flips into this state where we go into this desert environment. Okay, So this is an example of basically a threshold behaviour in the climate system where we've got gradual forcing, okay, when we get a gradual change, but then we get a sudden change. And this is one of the really kind of like dangerous things about kind of us playing around with the climate by pushing lots of CO2 into the atmosphere, is that the response of the climate system, okay, so the amount of warming, the amount of sea level rise, the amount of kind of like glacier collapse, that might not, or in fact that will not, be a nice linear response, okay? We may come to points in the future where we have these threshold responses where we get sudden, rapid changes in the climate system, which are very, very hard to reverse. Okay, so to summarise kind of the lecture, the whole lecture for today, even though it was yesterday because of the fire alarm. So we've had this gradual cooling into the icehouse world over the last 50 million years, and that has been driven by a whole bunch of different changes. So the amount of volcanism going, so the rate of mid-ocean ridge spreading, how much that determines how much CO2 from the mantle is getting up into the climate system, okay? And we've also had changes in weathering, okay? So if we increase the weathering by building mountain ranges like the Himalayas, okay, so that has allowed us to draw more CO2 out of the atmosphere. Okay, we might also get changes in the amount of carbonate precipitation, okay, so the amount of these kind of like shallow sea kind of things. That would also affect the amount of CO2 in the atmosphere. And also, it's not just things in our equation that matter at these kind of like shorter timescales than the very, very long timescales. We start to think about how the heat is redistributed around the Earth. Okay, so how efficient is it, the transport of heat from the equator to the poles? Okay, because that determines whether we can grow or melt an ice sheet, or how long snow lasts, or stuff like that. And that has important feedbacks in the climate system, which can then affect parameters like the albedo. Okay, so particularly changes in these ocean gateways, so that the opening up of the Drake Passage, so allowing Antarctica to be isolated, or shutting off the Straits of Panama. These are things that have altered how heat is transported from the equator to the poles. Okay, and then moving on to the shorter timescales of these orbital variability. Okay, so there are a whole bunch of different ways that the Earth's orbit and rotation can change. Okay, and these, importantly, don't really change the total amount of solar radiation. They change the distribution of that radiation, the distribution of that heat energy, so whether it's more on the poles or the equator, and importantly, which season that happens in. Okay, so do we get warmer summers and colder winters, or would you get more mild summers, more mild winters? Okay, so that determines, once again, some of these feedbacks which basically amplify these small changes. Okay, so things like changes in albedo, changes in the CO2 solubility in seawater, things like that. These are important amplifiers of these small forcings by orbital change. Okay, and then on top of this, these kind of like tens of thousand-year kind of changes caused by orbital variations, we have shorter-term climate variability. So the Earth's climate system is a very non-linear system, so it can flip between different states, and we saw that those states are not necessarily the same all around the world, so you can get regional variations as well. But these changes are driven by what we would describe as the internal dynamics of the climate system. Okay, so ocean circulation flipping between one state and another as we get kind of progressively more or less kind of fresh water coming into the Atlantic, for instance. Okay. And then, I guess, for kind of like the future terrifying kind of like climate change scenarios, this concept of thresholds in the climate system is really important. Okay, so that's the end of the lecture. Goodbye, and yeah, so if you're good night and all that kind of stuff. Okay.